Thank you very much. And I'm going to share the screen now.
Please.
And yes. Okay. Yes, I hope you were able to see that's my PowerPoint screen now. Are you able to see that?
Still in the process in my computer.
Okay.
Yeah.
Okay, let me double check.
Maybe you can try to close and try again.
Okay.
Yeah, now it's okay. We can see very clear.
Now you can see that, right?
Yes, exactly.
Okay.
All
right. Okay. Thank you very much. Firstly, I would say I'm pleased and honored to get this chance to talk in the ICAMT this conference. And thank you very much for the organization and invitation. And also, I'm happy to represent Singapore MRS, and I'm happy on that. Thanks for Professor Chadaway and Professor Tim White for the organization and the recommendation. Okay, of course, the organization committee and Professor Cartini, thank you very much. So I'm gonna today I'm gonna talk about the oxygen evolution catalysis on the magnetic oxides. And my name is Xu Zhichuan. I work from the NTU School of Material Science and Engineering. So this actually is quite interesting topic recently, kind of emerging, which in combination of electrochemistry and spintronics. And so the big picture of this research is about hydrogen as the energy carrier. So this has been discussed for many years. And so basically the energy rules, like we collect electricity from some sustainable energy resource like PV, and we use electrolyzer to split the water to collect the hydrogen, and then we use hydrogen as a fuel in the fuel cells, and then we get electricity. So this pretty much like stored energy and in form of chemical bonds of hydrogen. So for these overall technique rules, to produce the hydrogen, we have many ways to produce, but for water splitting, actually is most sustainable. Of course, if we use the electricity from the sustainable resource. And the bottleneck for the hydrogen electrolysis, let's say, is from the water splitting, actually is the oxygen evolution reaction site. So that says, although our target is hydrogen, however, the major energy loss actually happened on the other side, that is oxygen evolution reaction. So the overall efficiency can be limited quite a lot by this very slow oxygen evolution reaction kinetics. So if we look at the state-of-the-art electrodes for the OER, then actually we have to look at reaction media. In acid, we have to use noble metals because the acid is very corrosive and it makes the corrosion on the electrode materials. So we have to rely on the noble metals. But if we look at alkaline medium, of course, in that case, we have to change the membrane to a cation exchange membrane. In this case, we have a lot of a choice as electrode materials. We do not have to rely on the noble metals, and we can use transition metal and their based oxides. For example, nickel iron oxyhydroxide and perovskite oxides, and etc. And recently, there's a very, very interesting phenomena has been reported. it's a couple of years ago, and we actually found it as well. And so this is like, this phenomenon is like a magnetic field, which can enhance the OER. So that says if you apply a magnet on the working electrode, basically you will see the increment of your OER current. So that says the reaction kinetics actually get promoted, right? So this is a very interesting phenomenon. And so basically, that is because we assume the triplet oxygen is produced in this oxygen evolution reaction. Okay, so this means we have to look at the spin state of oxygen, dioxygen molecule. For example, we have triplet oxygen, we have singlet oxygen. So basically, triplet oxygen is ground state of oxygen. For example, oxygen gas, now we are breathing, that is a triplet oxygen. And the lifetime of singlet oxygen is very short. So basically, singlet oxygen have either one paired electrons in the pi or antibond, or two unpaired electrons, but they have a opposite spin direction. And for triplet oxygen, they have two electrons occupied on each pi antibond, and they have the same spin direction. So this, based on the Hund principle, and this is lowest under thermodynamic minimal states. So this is a ground state. So there are some modeling work they have predicted, and in the oxygen evolution reaction at the last step, if we release a triplet oxygen, this will be much easier than releasing the singlet oxygen. The energy difference can be more than 1 eV. So now this is actually recall the early work, the modeling prediction by the Jose Gricia. And he has done a very systematic modeling work. And basically, our opinion is like, if we produce triplet oxygen, if we look at the precursor of this OER, that is either the water or the hydroxide ions, for all the oxygen here, they are singlet oxygen. So in this case, the reaction at the two sides, reactants and the products, they are not balanced. So they have, they're not magnetic ordering balanced. They have involved additional an energy barrier for the spin selected electron transfer. So let's say how to understand it. So this is pretty much like, for example, if we want to produce a triplet oxygen, for example, to form a triplet oxygen bond, in this case, if we remove one electron, the spin down, like a green colored area here, if we remove the spin down electron from the first oxygen, we have to remove another spin down electron from the second oxygen. So that means this is an electron selected removal. Otherwise, we have to form a singlet oxygen. And in that case, thermodynamically, the reaction barrier will be increased. So this is like pretty much like exchange interaction at active sites. And further, Jose point out there's a spin selected electron transfer within the catalyst. For example, he used perovskite oxides as a models. So in that case, if we follow that kind of a logic, so pretty much we will draw the conclusion is like ferromagnetic oxides will be better than others. For example, we can classify that catalyst based on the magnetic property. Let's say ferromagnetic catalysts are better than antiferromagnetic or better than paramagnetic. So I would say as an electrochemist, I would disagree with it. I cannot say so because, for example, I can give you one example, the cobalt oxides and iron oxides. So basically, cobalt oxides is much better than iron oxide in the OER, oxygen evolution. However, the iron oxide, we know that is a ferromagnetic material, and the cobalt oxides, that's anti-ferromagnetic material. So this actually, against such a kind of conclusion, we drawn from the purely, from the modeling, right? So however, and the question is, how can we prove that additional benefit over here? As pointed here, let's say the triplet oxygen formation needs a spin-selected electrons. And this is additional benefit given by the ferromagnetic oxides. So that means we need a catalyst with the same surface chemistry, not change the surface chemistry. However, we need a more spin aligned, or let's say the more magnetic domain aligned in the ferromagnetic oxides. So this is something like magnetization. In this way, we can see the magnetization degree changed, and then we can correlate the result, activity result, and with the magnetization degree. And in this case, we can prove the existence of such a benefit given by the ferromagnetic oxides. So then we do the magnetization to test the OER under a magnetic field, right? However, we have to be very careful because the apply a magnetic field on the electrochemical system that will cause many other changes. So if we observe the difference, let's say observe the increment and a magnetic field, probably the increment comes from the resistance change of the electrode or the promoted mass transportation in the electrolyte, or say near the electrode surface, or some, according to Faraday law, there's a generated bias applied on the working electrode. So we must be very careful to exclude these things and then to draw a conclusion if that is true or not. Right. So basically, we employed 3 electrodes. They are cobalt iron oxides, spinel cobalt iron oxide, and cobalt oxides and iridium oxide. So the cobalt iron oxide, that is a ferromagnetic material, and this is a hysteresis loop of the cobalt iron oxides. And we can see roughly magnetization is 44 mU per gram. And crossivity is 887 Oyster. And cobalt oxide and iridium oxide, they are pretty much no magnetization because at room temperature, all of them are pretty much super paramagnetic, the paramagnetic, and very limited response to the external magnetic field. And then we tested OER and the magnetic field. Basically, you can say the setup, this is setup here, and this is the CV, the measurement. You can say the increment after applying under the magnetic field, we can observe the increment of OER for the cobalt iron oxide. But for the other 2 electrodes, there are no increment, all right? And then we suspect if there's any change on the electrode surface, for example, cobalt iron oxide surface get reconstructed, and then we observe the increment. So this could be a possibility. And then we use identical location TEM to observe the surface, exactly the same region before and after the test. And we found actually there is no significant surface reconstruction. So increment cannot be ascribed to the surface reconstruction. And then we did other measurements, for example, the magnetization and the demagnetization, right? For example, we measured activity and the magnetization, we observed the increment. And then what about we removed the magnetic field? And let's say materials will keep their magnetization degree a little bit, right? And we can see that this blue curve, they are maintained for a while. And then if we do a demagnetization, for example, you use the thermal interruption or something, or oscillation demagnetization process, we can observe the drop of activity back to the initial state. So this actually confirms the increment is due to the magnetization of cobalt iron oxide. And even interesting, we can find that there's a kind of correlation between the magnetic field strength and the increment of OER activity over here. And so all of these actually is we observed increment under the magnetic field. And then now we have to exclude other possibility to ensure that it's really from the magnetic field, all right? So let's say the direct answer about resistance change could be, which is impossible to affect the observed result. For example, the quick answer can be the no. So magnetic resistance, that is a resistant change of an electrode under the magnetic field. This is very common for the ferromagnetic material. The direct answer is this is not dominant because we can observe the pitch dependence, okay? And if that's because the resistant change of electrode, we should not observe such a pitch dependence. Instead, they will happen all the pitch value, right? Even in the acid, right? And then we actually measure the resistance change under the field. We found that there's no big difference, actually. And also we measured other reactions which do not involve the spin-selected electron transfer. We can observe that there's no significant increment under the magnetic field, right? So that says this phenomenon actually is unique to the reaction which involved the spin-selected electron transfer. And then we have to look at mass transportation to exclude such a possibility as well. We know that, okay, if this is an electrode surface and this is an electrolyte, and during the reaction, the charged species, for example, ions will have the movement on the electrode surface towards the electrode surface. So in this case, if I apply the Lorentz force, okay, if I apply a magnetic field, we know that the Lorentz force will be applied. So Lorentz force does not do work, but they will change the direction of the movement of ions, right? And if magnetic field is the same direction of ion movement, there's no Lorentz force. So basically, this is something known, and magnetic field and Lorentz force will improve the mass transportation of ions near the electrode surface. For example, they can shorten the diffusion layer. In this case, the limiting current can be improved, or let's say the kinetics we observed on the electrode can be improved. And this is a known size, right? And then we look back to our reaction, we can see that what we have observed over here is like, and if we assume the reaction over here is like hydroxide get oxidized to the oxygen, and then based on the equation diffusion limiting current equation, we can derive from there, and the limiting current is can be correlated with a field strength. So if we apply the field, definitely we will see the increment of a limiting current. However, I should remind us, it looks like the increment is by the mass transportation in promotion. However, it is not true, because if that is true, we should observe the similar to all the other electrodes, for example, uranium oxide and cobalt oxides, but we didn't observe that, right? And then we can do some other control experiment, for example, metal ion electrodeposition. We can apply the external magnetic field. So this is a very clear case. Lorentz force will work on that. We can see that when we have a magnetic field on, the limiting current indeed get increased, right? And again, we will emphasize that direction, it does not matter, because the real electrode surface is not very rough. So that says no matter which direction we applied, always we get a convection, which is caused by Lorentz force. So this has been widely observed for metal electrodeposition. They can observe the dendrite formation, etc. This is because of the magnetic field. So back to the OER. And also, I would like to include HER here. I would say magnetic field will not affect it, because the precursor, although we write precursor like ions, but in fact, the precursor is water, not charged ions. This is very unique for water, because water is solvent and also the reactant. So we know that the proton, actually the transport, or that ions transported within the water, is by the proton hopping. It is not the physical movement. So in this case, the Lorentz force will work very little on the mass transportation as we imagined it. So we can confirm the mass transportation won't play that important role over there. And then we can look at the last parameter, that is the magnetic flask. So magnetic flask, and this is because if you look at this potential state, this is our measurement setup. So basically, they form the circuit, right? And when we apply the magnetic field, when we have a field on and a field off, or even from nothing to some field, that means the field, the magnetic flux are changed within this circuit. And in this case, based on the Faraday's law, we know that a bias will be generated on this circuit. It can be bias applied on the working electrode. So in this case, that means although we apply the potential on the working electrode, the real potential applied on could be different because the magnetic field, right? So then we do control experiment again. So you can see that no matter where you place your other two electrodes, reference electrode and counter electrodes, where you place that in the magnetic tip or outside the magnetic tip, you are always changing the magnetic flux within the circuit. So it's independent the location where you place them. So you can always see the bias induced by this magnetic flux change. Okay, this is the number that changed. You can see that's roughly 0.025 milliampere per centimeter square. However, if we make the electrode big enough, we can see the magnetic field affected the current change actually is much bigger. This more than maybe 100,000 magnetic difference over there. So the change so the bias induced the Faraday law actually can be minimized by using the bigger electrode. So that is exactly what we are doing here. And based on the CV, we can see that. And the Lorentz force actually, the Faraday law, the induced bias actually had little influence on that if we use the CV approach. And so this is the same thing here. Again, we would like to emphasize that we didn't observe the similar on other electrodes, so we can confirm the increment on the cold iron oxide is indeed by something else. For example, because the ferromagnetic nature of this material. Okay, so now we can confirm the OUR enhancement is by the magnetization over here. So we can confirm, yes, that's additional benefit from the ferromagnetic catalyst. Right. So now let's see how can we extend this application, the principle, to the real applications. For example, because most best catalysts for OUR in alkaline, actually, they are not ferromagnetic oxides. They are oxyhydroxides, transition metal oxyhydroxides. You can see from these benchmark words, right? So all of them are not ferromagnetic. They're paramagnetic or they are anti-ferromagnetic, but under the room temperature, they are paramagnetic. So can we use that? Okay. So now we will introduce the pinning effect. We make the deposit by the reconstruction, control the reconstruction. We deposit cold iron oxyhydroxide on the cold iron oxide, which is ferromagnetic substrate, and we have paramagnetic top layer, which is a catalyst. And then we observed actually the much higher activity of these oxyhydroxide as compared to the oxyhydroxide without such a ferromagnetic substrate. So now what is reason caused that? We found that there's an interaction between them. So I'm going to skip this one. Okay, what's the interaction? This is exchange bias. It is a spin pinning effect. All right. So based on we made this magnetic measurement over here, we can observe the exchange bias for this kind of crucial materials. Like say we have ferromagnetic cobalt oxide and the paramagnetic cobalt oxides. So what is a pinning effect? This is actually a well-known effect in the physics. So basically, we have paramagnetic top layer and we have ferromagnetic substrate. If we attach these two layers at an interface, this interface could be a few nanometers. So at the interface, at the side of the paramagnetic materials, the spin can be ordered. They follow the ferromagnetic domain over there. So it's pretty much like they become the ferromagnetic, or they follow the ferromagnetic domain. So if we make, right, if we apply the magnetic field, okay, they actually will follow, because magnetic field can operate, or let's say manipulate domain direction of the ferromagnetic materials. And actually the spin at the interface, they follow the ferromagnetic domain. In this case, they can be indirectly operated, or let's say manipulated, right? However, of course, in the region much far from the interface, they totally independent, right? So now let's see, if we make this layer very thin, okay, just like the case I just shown cobalt oxide here, okay, if I make the top layer a very thin, just few nanometer, and then we are able to control the overall paramagnetic layer, the spin in the paramagnetic layer. So in this case, For example, exactly the model material we are talking about here is cobalt iron oxyhydroxide catalyst layer, which is the paramagnetic layer on the top, and we have ferromagnetic cobalt iron oxide as a substrate. So this actually exactly explains why we observed very high activity for this cobalt iron oxyhydroxide. Right. So this is a further experiments to prove existence of such a pinning effect. We applied magnetization. We can observe the top layer really follow the substrate, ferromagnetic substrate, and have increment under the field, and also after the magnetization. So, and this structure actually is quite stable. Yeah, because this is in the alkaline, and this two-layer structure is really stable. And after a few cycles, we can still observe such exchange bias. So in fact, as long as this structure exists and the pinning effect will not gone, the pinning effect will persist. So if I summarize, actually, the pinning effect actually can be used, okay, to promote non-ferromagnetic metal oxyhydroxide catalyst. So this is meaningful for the real application. For example, we can make coarser materials in the electrolyzer to promote the reaction. And now we can further investigate some science behind it. For example, how much the shell thickness and how much core size may affect such a pinning effect. So we designed the model electrode materials. We use iron oxide particles as a core, and we deposit nickel hydroxide on the surface, and then we do the CV cycling to enable the reformation of the surface layer to give the nickel iron oxyhydroxide, which is our catalyst. In this case, we can vary the shell thickness, and also we can vary the core size to see the domain effect, because we know the ferromagnetic material, they have domains, right? Okay, now let's look at the shell effect. Let's say how much the pinning effect can reach to the top layer, right? So we change the surface layer, the thickness of the surface layer, and from the 7 nanometer to 15 nanometer and to 43 nanometers, we can observe that actually thinner is better. So if the thinner, for example, 7 nanometer, the phenomena is significant, or let's say remarkable. But if the top layer is much thicker, we are not be able to see that. So this is inconsistent with the pinning effect, the principle of the pinning effect. They only happened at the interface, and that is around the range of a few nanometers. And then we look at the domain effect. And this is even more interesting, because if we employ the nanoparticles, which are single domain, and we will not be able to see any increment under the magnetic field, or let's say the magnetization, because there's no more magnetization can happen, because there are no more spin alignment over here through the magnetic domain change, right? And also we found actually without a magnetic field, a single domain particle, they actually can reach the highest activity, just like before, even without a magnetic field, they can have highest activity, because it's pretty much like the status of magnetization. So this is actually inconsistent with we have observed. If we apply magnetization, the multiple domain particle will become the single domain, and then activity will approaching the single domain particles. And this actually indicates much more for mechanism investigation, right? And then we have to talk about some details, how they happened on the surface. Because at the beginning, we talk about the electron selected transfer, a spin selected electron transfer, says for triplet oxygen formation, because we have looked at this pi sigma bond over here. We need 2 electrons with the same spin direction occupied in an HP pi p bond p orbital of oxygen, right? So, but how they happened in the details, right? And so, the secret, I would say, is in the over here, which is an important phenomenon, that is a pH-dependent enhancement, because we can only observe increment and the magnetic field in a high pH value, not low pH value. Okay, this is not a universal phenomenon for all the catalysts, of course, not for all pitch value. So this is an important radical because at a high pitch value, we know that the OH will have deprotonation process and give us activated oxygen ligand, which can be expressed at here, metal oxygen radical. So in this case, they do not form a pi bond with metal center. Actually, they form a radical over here. In this case, the d orbital and the pi orbital of the oxygen, they can have electron not in the chemical bond. In this case, they have their electron spin, the spin direction can be parallel. And in fact, this is true. They must be in parallel. So we can see the reference paper here. So this is totally different from the OH group, oxy species, in which they form pi bond and then electron these two electrons they have to in the opposite direction in the spin. So in this way, if we start from the radical, we can estimate or let's say predict the spin selected electron removal during the 4 steps OER if we follow the AEM mechanism, such kind of reaction pathway. Or if we look at the LOM or the I2M mechanism, this will be even easier because the neighbored radicals, they can directly form the triplet oxygen bonds. So that will give a much lower kinetic spiral. So we now actually suspect this is pretty much the dominant reaction pathway for this observed reaction phenomena. Okay, so finally, and I would say magnetization enhanced OER, I would say it is clear that spin played an important role for the triplet oxygen production, and the ferromagnetic oxides give an additional benefit in addition to the thermodynamics, right? However, to completely describe the surface, let's say what happened over there, we need to pay attention on the radicals. So now we are preparing the manuscript to further disclose the mechanism over there. Okay, so this is summary slides. I would say this is this is a very interesting phenomena, and that there's an emergent field, electrochemistry and spin electronics. And I believe the further investigation, for example, we can make the small devices, etc., or employ other magnetic materials, and for other reaction to investigate other reactions, to investigate possible spin involved electrochemistry. Okay, so these all of these work are made possible by my students. We have close. We put much great effort, and also my collaborators, and these 2 students of my group, they did a lot for this direction. And thank you very much for your attention. And this quick access code, you scan it, you can reach my group webpage. Thank you very much for your attention. Thank you.